Welcome back to the wonderful world of astronomy. This is the beginning of Chapter 18, The Bizarre Stellar Graveyard. And so far in this unit, we've been looking at the life of stars. It's not biological life, but we use the word life as an analogy. So in Chapter 16, you looked at the birth of a star. What happens to make a star become a star? And in Chapter 17, you looked at the life of a star as it goes through its processes with nuclear fusion. And then we got to the end of the star, what we call the death of the star. And so now in Chapter 18, we're going to look at the things that come from a dead star. And so first, let's remind ourselves of some things. First of all, review question. Our sun is considered which type of star? Do you remember? And it's a low mass star. Now you have to remember the categories. What does it mean to be low, intermediate, or high? And you can actually look down below and it defines for you those categories. We define a low mass star as less than 2 solar masses. So the sun by definition is 1 solar mass. So yeah, it is classified as a low mass star. There's intermediate mass stars, which are 2 to 8 solar masses. And there are high mass stars which are greater than 8 solar masses. So, next question, most stars are which type of star? And we learned back in Chapter 16 that nature has a preference of making low mass stars. And so by far, most stars are less than 2 solar masses. Next review question, at the end of a low mass star's life, its outer layers are expelled. The core that is left behind becomes which of the following? And hopefully you remembered it's a white dwarf. At the end of a high mass star's life, after its core becomes iron, it explodes in an event known as a supernova. Next question. At the end of a high mass star's life, the core that is left behind becomes which of the following? There are 2 of the following that are possible. And what does it become? Let's immediately eliminate brown dwarf. Brown dwarf is not the end stage of any star. Remember from Chapter 16, brown dwarf is something that almost became a star, but it wasn't massive enough, didn't get hot enough. And we can eliminate white dwarf because that's what happens at the end of a low mass star. So the answers are neutron star and black hole. The big picture. We learned by the end of Chapter 17, low and intermediate mass stars become white dwarfs. High mass stars become neutron stars or black holes. And those 3 objects are what Chapter 18 is about. So in this video, we're going to look at white dwarfs. In the next video, we'll look at neutron stars. And in the third video for Chapter 18, we'll look at black holes. Let's remember back to the Hertzsprung-Russell diagram that we learned about in Chapter 15. Remember that up and to the right, that's where it's bright and it's cool. Those are supergiants, and bright giants and subgiants. And then remember this strip here, 90% of stars are in the main sequence because that's where stars spend 90% of their lives. And then down here, the lower right, is low luminosity, yet hot. And those are the white dwarfs. So the topic for this video, white dwarfs, we're going to talk about ones that are right here. Look at this picture. This is a picture of Sirius. It's the brightest star in the night sky. And it's actually a double star. It's 2 stars, Sirius A and Sirius B. Now on the left is a picture taken with infrared light, and that's pretty close to visible light. And you'll notice there's the big one right here, that's Sirius A. It's the brightest star with visible and infrared. And then this tiny little dot down here to the left, that is Sirius B. It's a hot white dwarf. And because of its temperature, the wavelengths it gives off, it doesn't give off so much in infrared or visible, but it gives off a lot in higher frequencies. But you'll notice this difference here. Sirius A in infrared by far outshines Sirius B. Now, It all depends on what wavelengths you're looking at. So let's go over to the picture on the right. This is an X-ray picture as seen by the Chandra X-ray telescope. And you can see Sirius A, it's not so bright anymore because as a normal star, a main sequence star, it doesn't give off as much X-ray. It's not as hot. And so Sirius B, the hot white dwarf, outshines Sirius A in X-ray. And there it is again. White dwarfs are the remaining cores of dead stars, I want you to remember. And also, electron degeneracy pressure supports them against the crush of gravity. Remember back in chapter 16, we talked about brown dwarfs. And the question, as we think about stars and all kinds of stellar objects, what is it that holds it up against gravity? And with main sequence stars, it's the radiation pressure that's produced in the core, and in giants and supergiants there are shells, but they put out this radiation pressure that holds it up against gravity. But then in chapter 16 we talked about brown dwarfs. They aren't putting anything out. They're not putting out that radiation pressure, and it's the electron degeneracy pressure that supports them. Those electrons get squished so tightly together that they hold up against gravity. And that's the same with white dwarfs. We can look at this Hertzsprung-Russell diagram, and you can see a star like our sun. As it goes through its dying stages, it leaves the Hertzsprung-Russell diagram, so going up means it gets brighter. We talked about this in chapter 17. Moving to the right means it gets cooler, and it does this little bit of zigzag. Finally, it ends up as a giant. And then as it expels its outer layers, it peels away the outer layers, leaving behind a hot surface. The surface is now what used to be the interior of the star, and so it's very hot. That's why it's moving to the left. It's gaining in temperature, but eventually it all settles down. It calms down. It's going lower in brightness, and now it's moving to the right. It's starting to cool off, and so it's a white dwarf. And so it's going to continue to get cooler, meaning moving to the right. It's going to continue to get dimmer, meaning moving down. The size of a white dwarf. Very roughly estimate, you can say a white dwarf is about the size of planet Earth, which means having been the core of a star, it's going to be smaller than the sun, but significantly smaller because it's very highly compressed. And remember, back to chapter 7, when you learned about the solar system, and maybe again refreshed in chapter 14 when you learned about the sun is 109 times larger than the Earth in diameter. And so the Earth, very small compared to the sun, and this is the size of a white dwarf. Now, interestingly, a white dwarf with higher mass you might think would be a little larger because it's got more mass to it, but because its higher mass adds to more gravity, it squishes those electrons. Even though they're about squished to their limit, they get squished even more, and a higher mass white dwarf is actually a little smaller. So here you can see rough size comparisons. There's a limit to how massive a white dwarf can be. This is a product of quantum mechanics. We don't need to get too much into it in this class, but there is a limit. Once a white dwarf gets to be 1.4 solar masses, those electrons will not squish down any closer. So quantum mechanics says that electrons must move faster as they are squeezed into a very small space. They're not static, just sitting there. They're actually zipping around really fast, even though they're confined to a small space. If the white dwarf has a mass of about 1.4 solar masses, then those those electrons are so tightly confined into small spaces that according to quantum mechanics, they must be moving at the speed of light. But speed of light is a speed barrier. Nothing can get up to the speed of light. And so it all kind of falls apart. That's a barrier that it can't reach. So because nothing can move faster than light, a white dwarf cannot be more massive than 1.4 solar masses. We call that the white dwarf limit. We call it the Chandrasekhar limit. That's the official name of it. But for this class, we'll call it the white dwarf limit. Now, something very interesting happens when a white dwarf is close to another star. So imagine a binary star system. And here we have a painting. On the left is maybe a giant star, and on the right is a white dwarf. So they're in their different stages of evolution. And you can see in this painting, there's some mass transfer going on. The star on the left has grown to be a giant, and its outer layers are actually more gravitationally attracted to the white dwarf than they are to their own star. And so you get this mass transfer as the hydrogen, mostly hydrogen, but it falls onto the white dwarf. And that disk that you see in the painting is what's called an accretion disk. Mass falling toward a white dwarf from its close binary companion has some angular momentum, and the matter therefore orbits the white dwarf in the accretion disk. And imagine like water that's going down the drain in a sink. It sometimes doesn't go straight down the drain. It swirls around. It goes in a spiral. So that's the idea of an accretion disk. It's spiraling in, falling onto the white dwarf. Friction between orbiting rings of matter in the disk transfers angular momentum outward and causes the disk to heat up and glow. And so you can see in the painting, the artist has chosen to make the outer part of the disk red, the inner part a yellowish white. And the idea there is as the matter falls in, it gets hotter and hotter. Now, something interesting can happen as that matter builds up. It's falling onto the white dwarf. And so now for this picture, the left and right is reversed. So the companion star, the giant, is on the right. The white dwarf's on the left. And the white dwarf is building up a shell. Hydrogen-rich gas spills into an accretion disk and forms a shell of hydrogen on the white dwarf. Well, that shell is very, very hot, and if it gets up to 10 million Kelvin, it can undergo nuclear fusion. So for a very brief moment, this star comes back to life with a burst of nuclear fusion, and that's what's called a nova. Now, nothing happens to the white dwarf itself. It's just that shell of hydrogen gas that's been built up. A nova occurs when the shell becomes hot enough for a burst of hydrogen fusion. This image from Hubble's Space Telescope shows blobs of gas ejected from a nova. The bright spot at the center of the blobs is the binary star system that generated the nova. The nova star system temporarily appears much brighter, and the explosion drives the accreted matter out into space. So here's a question. What happens to a white dwarf when it accretes enough matter to reach the 1.4 solar mass limit? So let's say a white dwarf, maybe it's 1.3 solar masses, and it's got a companion. It starts building up hydrogen. It starts building up hydrogen. Then it gets to 1.4 solar masses. And I showed you earlier in the video that because of the limits of electron degeneracy pressure, it cannot sustain that 1.4 solar masses. So let's think about what's going to happen to it, because it can no longer hold that. And let's assume it's not going to have a nova. It doesn't blow off that outer layer just because the outer layer, let's say, does not yet get hot enough to have fusion. So what's going to happen? And some possibilities, maybe the entire white dwarf explodes. Maybe it collapses into a neutron star. That's a reasonable bet also. Another, it gradually begins fusing carbon in its core. Well, the answer is A, it explodes. So if a white dwarf starts building up the matter, it doesn't go nova, it doesn't blow off the outer layer, the entire star, the entire white dwarf will just explode. It will spontaneously undergo nuclear fusion and become a very powerful bomb. And that is actually called a white dwarf supernova. Now let's make sure we have our vocabulary straight. You've already learned one type of supernova, and that was a massive star supernova. So remember at the end of chapter 17, you learned the life of a high mass star, and at the end, its core becomes iron. The outer layers, they collapse in, they rebound outward, and that is a supernova. And now we're going to call it a massive star supernova. So that's where the iron core of a massive star reaches the white dwarf limit and collapses into a neutron star, causing an explosion. But what I'm talking about now, when a white dwarf exceeds, or it gets to it and then exceeds 1.4 solar masses, it can't handle it, it will explode. Carbon fusion suddenly begins as a white dwarf in a close binary system reaches white dwarf limit, causing a total explosion. So we see supernovae in the sky. They are these bright flashes, and they eventually die away. And astronomers want to figure out what type of supernova, what type of event did we just see? Well, they have common features, their light curves do. As you look at this graph here, the vertical axis represents luminosity in solar units, how bright the event is. And notice these numbers, 10 to the 7th, that's 10 million, 10 to the 8th is 100 million, a billion, and 10 billion times the luminosity of the sun. So the bottom of this graph is above the top of a Hertzsprung-Russell diagram. The Hertzsprung-Russell diagram only went up to, I think, 10 to the 6th solar units, or 1 million times the brightness of the sun. So this far exceeds, this gets into thousands, millions of times the brightness of the sun, even billions of times the brightness of the sun. One way to tell supernova types apart is with a light curve, such as this, showing how the luminosity changes with time. So with a massive star supernova, you can see it spikes up, and then it always has this general trend where it'll dim down and kind of stay a bit with a slight decrease, and then a sharp decrease, and then a slight decrease, and it eventually goes back down into saner levels of luminosity. A white dwarf supernova, on the other hand, in the red curve, it's much more dramatic. It can be much brighter. 10 to the 10th, so we're talking roughly 10 billion times the luminosity of the sun, which is going to be comparable to the luminosity of an entire galaxy. And it'll have a sharp decrease and then eventually peter off right there. You will not, for this class, need to know or be able to discern the differences, but this gives you some insight into what astronomers look at as they're trying to discern different bright events that they see in the sky. You can see that after several months, maybe as much as a year, it eventually dwindles away. So when there is a bright thing in the sky, was it from a white dwarf? Was it a nova or was it a supernova? Well, just the prefix there, super rather, means it's much, much brighter. So a comparison between them, supernovae are much, much more luminous than novae, about 100,000 times. A nova, remember, is where hydrogen fuses into helium in a layer of accreted matter. And so it's just that layer that's built up, that outer layer. The white dwarf itself is left intact, whereas a supernova is the entire white dwarf just blows up. So you can expect it's going to be much more dramatic, much brighter, and there is nothing left behind. That is the end of section 1 on white dwarfs. Let's review what have we learned. What is a white dwarf? A white dwarf is the inert core of a dead star. Electron degeneracy pressure balances the inward pull of gravity. And what can happen to a white dwarf in a close binary system? Matter from its close binary companion can fall onto the white dwarf through an accretion disk, and accretion of matter can lead to novae and white dwarf supernovae. And that is it for white dwarfs for now. I hope you have a great day.